Good morning, everyone. Okay, what do you see in this slide? What do you see in this slide? Packages? Okay. Different packaging materials. What kind of packaging materials you see? Glass, polymer, paper, paper and metal. This lecture and next few lectures would be different than what we had last 2 days. Last 2 days we covered mostly processing, and next few lectures would be around packaging. So other than these four materials, what you see, do you think any other material we use for packaging of food? You see four here, right? Metal, glass, polymer, and paper. Anything else? Sorry? Leaves? Well, this is also part of the cellulose-based packaging, right? Paper is cellulose-based, and what examples you're giving, those are also cellulose-based packaging. That's also cellulose-based. Tetra Pak is a good example. It's not just paper or cellulose, it's a combination of cellulose and plastic. So sometimes we use these packaging materials individually, and sometimes we have composite. It's a combination of two. What kind of relevance of packaging you see in food industry? What is the importance of packaging? Protection from what? External factors.
Prevents the internal moisture and gas to exchange with atmosphere.
Okay. Easy transportation, branding,
Prevents contamination.
prevent contamination, advertising,
Some information about the food is
labeling, yeah, some information about food. Okay, all of the correct answers. These are all functions and purposes of packaging. So let's get started. But before we start, if you look at this, the title of this lecture is permeation. Do you know what permeation is? Sorry? Ability to move.
through some layers.
Ability to move through a membrane.
We are referring the permeation of gases through this packaging materials. So what kind of packaging materials will allow transmission of gases? Polymer, paper. Most of the time, paper is moisture sensitive, so usually it is used for the dry products. And in case if you want to use with the wet products, so most of the time you would have inner lining would be from polymer. So it's like use as a composite packaging if you want to use for the wet products, such as example for Tetra Pak. So primarily we are talking this permeation through polymeric films. So this brings us to polymer packaging. Polymer packaging, these are some of the advantages of polymer packaging. It's a low density material, resistance to breakage and moisture. This is comparing with glass and paper. Food ingredient resistance, this is again comparing with some other material. Fabricability into various shapes, again comparing with the glass and metal cans. You do not have a lot of different shapes made of glass. It's mostly cylindrical jars or containers. Transparency and colorability. Of course, glass is also transparent, but paper and metal is not transparent. and you can have a variety of colors, which is not very easy to do with other packaging materials. Availability in wide range of grades. It means that you could tailor-made mechanical, thermal, or barrier property for polymeric materials, which you don't have choice with other materials. And of course, polymer is compatible to some of the processing technologies. In fact, these processing technology would not be possibly commercialized if you didn't have polymer packaging. As you know, with the microwave, metal is not compatible. Glass is a very high density material. It's a lot of liability. It can easily break, so it's not a choice of material. Same with the pressure assisted or pressure processing, high pressure processing. You cannot use glass. You need a flexible surface for pressure to transmit from medium into the food. So how does the permeation happens in or through polymeric films? So it says that all packaging polymers are permeable to some degree to gases and vapors, and these polymer packaging provides a wide range of permeability for different applications. Because we have wide variability, it provides opportunity for designers to optimize the barrier property for various applications. So the requirement for the gases for different food product is different, and this allows you to select appropriate polymeric films, or if not available, then it allows you to design film which is suitable to give you maximum shelf life for a given food product. And so this is the example giving the permeation. The way it happens is that it is not simply like you have pores, like in a filter, that that gases are just walking through those pores. What it happens is that the gases are absorbed at the surface, and then they move or diffuse through the thickness of that film, and then they are desorbed, right? So it's not like a simple holes, like you have a coffee filter or tea filter. It just, water molecules are just passing by. In this case, it's absorption, diffusion, and desorptions. So the importance of permeation through polymeric packaging is that it can influence the keeping quality of your packaged food, because different food products have different requirement, and if you do not allow the appropriate amount of gas exchange or vapor exchange, then it's going to affect the keeping quality or shelf life of your product. For example, lipids can get easily oxidized and produce off flavors. Sometimes oxygen can also result in loss of color and nutritive value. And if there is a exchange of water vapor, then you could lose moisture, or you can gain moisture. And if you gain moisture, it can result your product in textural changes, and also it can allow some microbial growth as well. However, in case of modified moisture packaging of fresh produce, actually transport of gases and vapor is highly desirable. So in some cases you do not want, or you want to minimize the gas exchange, while in other cases you want to have this gas exchange to have a higher shelf life. Can you think of why we need transport of these gases and vapor in the case of modified moisture packaging? By the way, do you study food packaging as a course in your BTech? Okay, have you done that, or have you done? Okay, so then you should be able to give this example. So tell me, where do we need and why do we need in case of fresh produce?
Sir, because the fresh produce is still respiring, so we need a combination of oxygen and another gases so that it can respire, and even if it's ripening period can be extended for its longer shelf life.
Let's say if I take a fresh fruits, mango, let's say, and I put a bag where I have, let's say, no exchange of any gases, what will happen?
So the ethylene, because of the ethylene gas production, it will ripen very fast, and then extra ripening.
Okay, that's the case of fruit, they are ripening. Many vegetables or some of the fruits, they do not ripen. Then what happens? That example is correct. But let's say to extend that, some vegetables and fruit, they do not ripen. Then what happens? So that's from the ethylene perspective.
There will be anaerobic growth over there because they need to respire because they are living tissues, and if they don't get oxygen and other gases, then they will start decaying.
Correct. So if in case, if you don't allow oxygen ingress in the package, it's going to consume all the oxygen inside the head space during respiration, and it's going to produce a lot of CO2, it's going to build up a lot of CO2. And if it is deprived from oxygen, then you have anaerobic respiration, and then there's a possibility of growth of anaerobic bacteria. So you start having anaerobic fermentation in some cases. And of course, if it keeps producing CO2, then you're going to build up a lot of CO2 inside your head space. So in order to have the appropriate shelf life, you need certain amount of gas exchange. We know what amount of respiration is taking place. It means that at what rate it is consuming oxygen, and we also know at what rate it is producing CO2. So if we ask you to select a film for that given product, how would you select? What would be the oxygen transmission rate of that film, and what would be the CO2 transmission rate of that film? Can you think of it? Of course, you had to do a lot of quantitative analysis, but just give me simple answer. How would you do that? Do you think that we would select a film so that it allows significant amount of oxygen to come in, or whatever CO2 is being produced, just allow it to, transmit through the film into the atmosphere? No, different fruits and vegetables, they have different optimal gas composition in the head space, and through the packaging film, you want to maintain that amount of gas in the head space of the package to minimize the respiration. You still want to have some respiration, but you don't want to have the same rate what happens normally at room temperature. So this is how you slow down, and this slowdown actually extends the shelf life. So we will look that in later slides. Yeah. It is telling us here in this slide that freshly roasted coffee degassing is necessary to prevent excessive pressure buildup. Have you studied coffee roasting in your? Why do we do roasting before packaging?
So it develops flavor in the coffee.
It develops in the flavor coffee, and then after roasting, if you immediately pack in the bag, what happens?
It forms cakes.
Actually, it produces a lot of CO2. And if you do not allow the CO2 to escape from the bag, then it's going to blow up. So what they do, they have this kind of a valve. If you see any Starbucks coffee, if you buy it's aluminum-based packaging, foil-based packaging, because that can prevent moisture exchange and the gas exchange. But they do provide what they call one-way valve. This allows us to, whatever CO2 is being generated inside can escape through this valve. As you can see here, this is inbuilt in your packaging film. Okay, so this way packaging can help you to have some amount of CO2 exchange, so that you avoid the building of excessive pressure inside the bag, otherwise it's going to blow up. So gases and vapor, what is the difference between gases and vapor?
Above the critical point, it will be a gas.
No, gas is not gas is not just limited to vapor, but like they have another oxygen, nitrogen, but vapor is just limited to water in the gaseous phase.
Just water, not anything else?
And quite bit of this
So at normal condition, vapors are condensable. It could come from organic solvents as well, but these at normal pressure, these gases are not condensable. Of course, under extremely high pressure, you can condense, but the normal atmosphere pressure, these are not condensable. So these are the gases, and vapors are condensable. So gases have low boiling point, and they are not condensable and exist in gaseous state at ambient temperature. The example of the gases which are of interest to us from the food packaging point of view is O2, N2, hydrogen, CO2, and so on, and they all follow Henry's law. We will see what we mean by Henry's law. And the permeabilities and diffusivities are constant and not concentration dependent. You understand what does it mean, not concentration dependent? You remember when we were given the inactivation of microbes, it depends upon the concentration at that time. Yeah, so the diffusivity does not depend upon the concentration of gases. So if the gas concentration is different, the diffusivity still remains same. The same amount of gas will pass through. But that's not the case for the vapors. In case of vapors, permeability and diffusivity of those vapors depends upon the concentration of that vapor. So let's say, what is the Henry's law? Henry's law is one of the gas laws. I'm sure in thermodynamics you would have studies like Boyle's law and Charles' law. It says that at a constant temperature, the amount of a given gas that dissolves in a given type and volume of liquid is directly proportional to the partial pressure of that gas, which is in equilibrium with that liquid. In simple words, it is equivalent to the solubility of a gas in a liquid is directly proportional to the partial pressure of a gas above that liquid. The perfect example is for this carbonated beverages. And solubility is the one which has the trend against temperature, which is different than for all other thermophysical properties. So for example, let's say specific heat. Higher the temperature, higher the specific heat of the material. But if higher the temperature, what will be the solubility of the gas? Actually, it will be lower. The solubility of gases decreases with temperature. So lower the temperature, higher the solubility. And that's why I'm sure you all have experienced that these beverages taste good at the lower temperature, because whatever the gas is there, it is soluble in your liquid, and that gives you bubbly effect. So if you bring it to the room temperature, what happens to those gases? They come in a head space, right? If a lot of gases come in a head space, some of them can permeate out of the package. So that's why even to preserve, it is better to preserve these, at low temperature. And that's why you have shelf life of 3 to 6 months of these bottles, because at room temperature, the level of gases which are dissolved in this liquid are less, because most of them are in the head space. So that's why when you cool it down at refrigerated temperature, they get solubilized, and then when you open, they give you good taste. So mathematical description of this Henry's law is that concentration of this permeant is equal to solubility coefficient multiplied by the partial pressure. Why we have this kind of relationship? Because if you have to characterize the gases, measuring concentration is not very easy, right? Let's say in a bottle, if you have a gas, if you want to ask you how much is the concentration, it is very difficult to measure. It's not very straightforward. But measuring the partial pressure or pressure of the gases is very straightforward, right? So that's why mathematically in an equation we would write concentration, but actually we measure experimentally the partial pressure or pressure, and then we multiply solubility to get the value of concentration. And of course it follows the Lorentzian relationship because the solubility is constant. So pressure versus the concentration is the linear relationship. So vapor, they are basically condensable at normal temperature, normal pressures. And the condensation of vapor, specifically in case of food, we are not looking at the other organic solvents, we are looking at the water. And it can cause fogging on the package surface, and that could result in microbial growth. Water vapor and other organic vapors, as you mentioned, often deviate from the ideal behavior, which means that its permeability and diffusivity are actually concentration dependent. For example, in the case of ethylene vinyl alcohol and nylon, because both are hydrophilic polymers, unlike many other polymers which are hydrophobic. So what are the mechanisms of transport of these gases and vapor through polymeric films? So you could have permeation or you could have a leak. And permeation, we refer to the property of the plastic film, and leak is actually pinholes or channel leaks, which are basically defects, right? So permeation is actually property of polymeric film, and leaks are where actually defects. But when you are really doing the experimental measurement, what it measures is both actually, the permeation as well as some of the leaks, if there are some pinholes or some cracks in your polymer. Okay, have you ever measured oxygen transmission rate or water vapor transmission rate through polymeric film through any experiments? Okay, so what is the sample size you take? It's significant, right? Could be 5 centimeter or 10 centimeter, in that range diameter of film. So in that film, if when you mount it on your instrument, you will be measuring permeation as well as leaks or cracks in that, and that's the overall transmission. So that's what you get from that is the overall transmission rate of gases or vapor, whatever setup you have. Yeah, so this is what we saw previously, is that you have the higher concentration of a gas, it is absorbed at the surface, and then it diffuses through the polymeric film thickness, and then it is desorbed or is released this side, and then of course you have lower concentration because that's the driving force, and this side you could have any food product. So if you look at the mathematical representation of that diffusion, so the diffusion happens from high concentration to low concentration. We describe that diffusion using Fick's first law, where J is the diffusion flux is equal to minus diffusivity, and it is given AB. You know what is AB means?
Diffusion from A to B, component is A to B.
What is A and B? Usually it is referred as the diffusivity of material A into medium, or material A into medium B. So that's the diffusion coefficient or diffusivity, and C is the concentration of your permeant which is diffusing, and X is the distance in the flow direction. Why we have negative sign? Correct. So this concentration dC over dx, you write low minus high over the distance, and then low minus high will give you the negative, and the negative gets cancelled. Okay, so this is the basically Fickian behavior and the concentration independent diffusion coefficient. And as we said, in case of a vapor, it is non-Fickian. So then you will not use this equation, you will use something else. And so in this case, you would see this is the steady state, right? There's no time term in this equation, right? So it's a steady state diffusion. But initially when the diffusion starts, it takes some time to come to steady state. So that unsteady state, how do we describe the diffusion? Let's take this film. I'm sure most textbook you have seen that, and take the flux at any point in the film, and take the flux at delta x distance. So this is the flux multiplied by area, which will give you the volume, amount of the gas here and the amount of the gas here. If you take the difference then that difference is the one which is being accumulated in this small volume, and that's what it's saying. The concentration multiplied by area, and that distance, that gives you volume, and is being accumulated with time here, right? If the whole term is 0, then whatever coming here is going through this, right? And if you take this, as you can see, both sides, all A area is constant because we're considering the constant area through the film, diffusion is taking place. And then take the delta x, divide by this, so you would have this, the change in the concentration with respect to time. So this is what you have, change in the flux with the dx, which is the change in the concentration over time. And as we saw from the previous slide, flux you can write minus dAB, or in this case I just taken out the AB, just the d, dc over dx. So if replace this j with this, you will get this term. So this is describing the diffusion with respect to time. Okay, so initially you would have, both sides the same concentration of the gases, and suddenly the concentration of the gases are, the partial pressure is different this side, let's say higher concentration, and then slowly the gases start diffusing. So within the film itself you may see this kind of a profile, and eventually you have this concentration this side and this concentration this side, and this becomes the steady state, and that's what it is described in this equation as a steady state. So let's recapture this. So diffusion rate, so the total quantity flowing Q is the flux multiplied by the surface area, which can give you, wait a minute, just something is not showing up. Okay, yeah. So this is the equation, we saw that from previous, and as I said, it's from a steady state situation. This is the Cl minus C0 over L, so this is a concentration difference. So the Q is equal to, if you combine these two equations, you will have dA, which is the diffusivity multiplied by surface area, and the concentration difference over thickness. Rather than x, we are writing L. And from Henry's law, we know the concentration is partial pressure multiplied by the solubility. So if you replace this, then you will get this equation, and eventually this solubility multiplied by diffusivity will give you P as a permeability. Why we are converting this concentration into permeability? This is a partial pressure.
Because the concentration in partial pressure only drives the concentration.
It is simple to measure. So measuring concentration directly using instruments is difficult. So we have a lot of sensors to measure partial pressure. So that's why rather than measuring the concentration at the surface, we measure the partial pressure, one side of the film and the other side of the film. Yeah, so this is your final equation. Q, the amount of gas being exchanged, is equal to permeability of that film multiplied by surface area of the film, and delta P, that's the partial pressure difference. So for example, if you do vacuum packaging, right, inside you have absolutely no gas, and if you're looking the diffusivity of, the gas exchange, oxygen exchange from outside to inside, what would be the delta P? What is the partial pressure of oxygen in the atmosphere? 0.21, if you think in terms of the atmosphere pressure. It's a 0.21 of in terms of the kilopascal, 101.310 kilopascal multiplied by 0.21. So whatever units you use, you can use whatever the partial pressure of oxygen is outside and whatever is the partial pressure of oxygen inside the package. So that will give you the delta P, and this is the thickness of the film. This is the surface area of your package, and if you know the permeability of oxygen for that film, then you can calculate how much oxygen is getting into the package per unit time, correct? Why this information would be important? Because let's say if you have any product which can react with the oxygen, let's say powdered milk, it has a sufficient amount of lipids, and lipid can react with the oxygen and have lipid oxidation and create the rancid flavor. And then let's say if you have 1 kilogram of milk powder, it has certain amount of fat. You would know what is the composition of fat in that milk powder. And from experiment and sensory testing, you would have determined how much fat has to be oxidized so that it will give you off flavor. And in order for that fat to be oxidized, how much amount of oxygen you need to oxidize that amount of fat. So if once you know that how much oxygen is needed, then from here you can find out at what rate oxygen is coming in. Once we know at what rate of oxygen is coming in, and we know how much oxygen we need in order for fat to be oxidized, then you can find time. And that's actually your shelf life. In case that time is very small, and then you really want, longer shelf life, then what you would do? Yeah, only thing you can change here is the permeability. So go for the film, which has a higher oxygen barrier properties. So this is how these kind of mathematical description can help you to either design a film or select a film. So in terms of the selection, whatever films are there, you just see what permeability with respect to oxygen it has. You plug it here and it can give you time. Or you want a certain time in terms of the shelf life, 1 year, 2 years. So then you put that time in this equation and then you say, oh, what would be the permeability I need for that film that will give me that much shelf life. Okay, so this desorption and adsorption of permeate depends upon the behavior of permeate molecules and also the relative strength of interaction between permeate and permeate. So this is the interaction between the molecules. In this case, it's the oxygen or CO2 which is permeating, or the interaction between that permeate molecule and polymer, and what is the interaction between polymer to polymer. All these factors would influence how much gas is really transmitting from one side of film to the other side of the film. In most situations, we do not have only single layer. In most cases, we have multi-layer films. Why do we have multi-layer? You know what is multi-layer we are talking about? That you are combining polypropylene, polyethylene, and nylon, PET. Why do we have this multi-layer structure? Can you think of it?
All the individual packaging metals have their own strength. So if we need a packaging metal with all those strengths, we have to put it on layers and layers so that all the
See, for example, you gave to improve the barrier property, if you have a film which is low barrier, if you combine with the high barrier, what would be the resultant barrier property? Will be high barrier or low barrier or somewhere in between? The overall transmission will depend upon the high barrier, not on the low barrier. But the permeability would be somewhere in between, because that accounts for the thickness and surface area of the film as well. So that, I'm sure this series resistance, you would have studied that concept from electrical circuits. So if you take this equation, Q is equal to PA delta P over L, you can rearrange this delta P over L over PA. And delta P is the driving force, and this is the resistance. Okay, and you can add this resistance in the series. So if you have multi-layer film, they have different thickness, L1, L2, L3, and of course surface area is same, and the permeabilities are different, so you can add up in this way, and then the overall you can result the permeability of this multi-layer structure would be in this form. So in terms of other terminology for the permeation, sometimes we say transmission rate, and transmission rate is Q over AT. Q is the amount of gas being permeated per unit time divided by surface area. So this is Q, the total gas, cubic centimeter, A is surface area, and T is time. If you divide this transmission rate with partial pressure because the overall, the transmission would depend upon the, so in this case, this transmission rate is fixed based on the partial pressure. But if you divide that with the partial pressure, what we call is the permeance of the film. But that if you divide or multiplied by thickness of the film, then it gives you permeability. Why do we have all this different type of description for the same transmission? So permeability is an intrinsic property of the material. But for the same material, the amount of transmission could depend upon the partial pressure. So this is how we differentiate. So when we are comparing from one material to another material, we would use probably permeability because that's the intrinsic property of the material. So one material is better than other material, we would compare using permeability. But for the same material, the amount of gas exchange would depend upon whether you are taking different thickness or if you are taking different partial pressure of the vapor or the gases on different side of the film. Now this table is showing you some of the oxygen permeability and CO2 permeability and water vapor permeability of different films. I want you to look at it that for polyethylene, the low density polyethylene, oxygen permeability is lower than the carbon dioxide permeability. Can you think of it why any given film will allow more transmission or permeability of CO2 compared to O2? Because CO2 is larger molecule than the oxygen.
The structure of the molecule differs. Even if it's a larger molecule, the bond angle varies maybe because of that.
No. So think about permeability, diffusivity, and solubility. What is the relationship?
CO2 will have more permeance.
Permeability is equal to what? Diffusivity multiplied by solubility. So actually diffusion of CO2 is much smaller than the oxygen because a bigger molecule in the same polymeric structure, it does not diffuse very quickly. Actually oxygen diffuses much faster than CO2, but the solubility of CO2 in almost all synthetic polymer is much higher than the solubility of oxygen. Because of that, the total permeability, which is the diffusivity multiplied by solubility, is higher. And among these all polymer, if you see which polymer is giving you the best barrier property in terms of the oxygen, it is the ethylene vinide alcohol, especially when the relative humidity is 0. So at low relative humidity, this polymer gives you the best oxygen barrier property. But because it is hydrophilic polymer, if you allow some amount of relative humidity around that polymer, is going to absorb a little bit of a moisture, and when it absorbs, then this polymer is going to get plasticized and is going to increase the free volume properties. And because it increases the free volume properties, it means that the space between molecular chains is increased, and then it allows more oxygen to go through it, so it reduces its barrier properties. So this figure is showing you in terms of the overall water vapor permeability and oxygen permeability. So as you can see that this polymer has the lowest oxygen permeability, but its water vapor permeability is higher than many other polymers, simply because it is hydrophilic polymer. And if you want the lower water vapor permeability, so these are the polymer PVDC, OPP, which is oriented polypropylene, and HDP, high density polyethylene, and PP is the normal polypropylene. So this diagram gives you a good indication depending upon the requirement for your material. If the material does not have a lot of lipids, it does not react with oxygen, but if it reacts with the water, you don't want it to have a lot of moisture migration within the package, then you may be selecting these films. But in case if your product has a lot of lipids and you want to minimize the oxygen ingress into the package, then you would be selecting these kind of films rather than this. So depending upon your requirement for your food product, this diagram can guide you what material to select for. And of course, if you need both barrier, oxygen and water vapor, then this PVDC and this EVOH are material for your selection.
Sir, can we use the same conditions for other storage conditions? Because this one is only for 38 degrees C and 90% RH.
Oh.
Low temperature, low humidity, or high temperature. This one is high temperature, high humidity.
So this permeability, when you measure under a certain condition, right? This condition, this is kind of like a ASTM, American Society of Testing Material. It's like when you measure the moisture content or protein content, fat content, you have some standard AOAC, right? They give you protocol how to measure, right? In a similar way, American Society of Testing Materials, they have given a protocol to measure these permeability at these conditions. So then you can compare from one film to another film. But definitely the permeability is affected by temperature. So higher the temperature, what will happen to permeability? Higher the permeability. Why it will be higher permeability? What happens to the polymer if you increase the temperature? What could happen? You would increase the space between polymeric chains. If you increase the space, then it's going to allow more gas to transmit. So for more sophisticated design, you would use these permeability value based on what were the storage condition. So if your storage condition is higher than this, then you want to measure the permeability. And then the change in the permeability of this polymer may not follow exactly same trend with respect to temperature. Maybe when you increase the, let's say, we're talking about oxygen permeability. So let's say look at PVDC and this. So at 38 degrees C, EVOH has lower permeability than PVDC. But then let's say you increase temperature from 38 to 60. It is possible that the permeability of this EVOH become higher than PVDC. Both will increase, but the increase this may be much higher than this. I don't know. So depending upon whatever value you get at that temperature, then you should have the guidance of that kind of a map you should generate at that temperature, and then you have the selection from that map.
Because in industrial conditions for dry foods, mostly you are using less than 20 and less than 70 RH. And for fresh, you are higher.
So I know why they try to select 90% relative humidity. Even though your product may be dry, right? Inside your package, maybe you have very low relative humidity, because if the water activity of a product is very low, the partial pressure of vapor in that head space would be also very low, because your product water activity is low. But outside atmosphere, sometimes there is a possibility that it's highly humid environment. You would ideally like to store low relative humidity environment, but for whatever reason, if it is you have higher relative humidity, then you will have higher transmission of gases, or permeability of that film will be higher. So that's why they try to measure or give value sort of more safer side. So that's why they have measured at 90% relative humidity. So other factor which governs the permeation, as we said, nature of the polymer. For example, the polarity, molecular structure, chain-to-chain packing can influence the barrier properties. Polarity can result in cohesive energy differences. and then that can also affect the diffusion and permeation. Crystallinity of the polymer and the molecular orientation of the polymer can also influence the permeability. For example, most of the polymers, they are partly crystalline and partly amorphous, right? So the crystalline structure would not allow any gas diffusion through it, but the amorphous structure will allow. So crystalline structure where the atoms are really organized in the lattice format, and there is absolutely no space between that for gases to permeate. But the amorphous part of those films or the polymer is a polymeric chain entangled somehow, and then in between these entangled chains you have always some space, so that allows the gases to transmit through it. But then if you can have the molecular orientation, that if you align those in a chain in a very net form, then you can also minimize the gas transmission. So the polymeric structure can significantly influence the amount of gases it would transfer through it. And of course, if you allow some addition of additives in the polymer, what kind of additives we have in polymers? Do you know additives and plasticizers? So actually the natural native polymers like polypropylene or polyethylene, all these polymeric resins, it is not very still easy to stretch the film. So we allow some additives into it to plasticize that polymer. And plasticization means like when you have this wheat flour, right? Wheat flour, you cannot stretch a film from it. How can you stretch the film? Like how you make chapatis or bread, you add some water, right? You add some water and then you plasticize your starch molecule in your wheat flour, and that allows you to stretch that dough and make a film, right? Thin layer. In the same way with the synthetic polymers, of course we do not add water into it because they're the hydrophobic polymers. So we add some other plasticizers which can help us to stretch that film. They help us to improve manufacturability. Although it improves the manufacturing ability, but then also they increase the space between molecular chain, and then it can increase its permeability. So the type of plasticizer you would select can also influence the permeability of those polymers. So this is a giving example in terms of the interaction. So if there's no interaction between polymeric chain, there's no bonding, then you can have permeant molecule, it can simply diffuse through it. But if there is an interaction between polymeric chain, then it will not allow the diffusion from this part because there is a bonding, and then molecule has to take a longer path of diffusion. If the longer path of diffusion means time taken to diffuse the same distance will be more, which means that the diffusivity is lower, right? Because diffusivity is the distance traveled divided by time. Rather than in changing the distance, you are increasing the time so that your diffusivity would be lower. The nature of permeant can also influence diffusivity. So molecular size of the permeant, the bigger the molecule, it will have a hard time to diffuse through that polymeric structure. And if it has a chemical affinity, if that polymer has a lot of affinity to that gases or permeant, then it is not going to allow it to diffuse very quickly. And of course, the longer molecule will have the lower diffusivity again, because they had to find a path, a gap between those polymeric chain in order for it to travel through that. And higher solubility also makes the difference in overall permeability. If it's more soluble, it's going to retain there rather than moving through the polymeric structure. So again, this is, it's the same table giving you, like a previous one, diffusivity value, and it is telling you what are the functional group which actually renders the barrier property to different polymer. So when they want to really improve the barrier property of different polymers, they try to add some functional group so that they can reduce the diffusion or improve the barrier properties. Yeah, so this is the famous Arrhenius equation. and showing you, as we saw that the reaction rate constant depends upon the temperature. In the same way, the permeability also depends upon the temperature, and it also follows the Arrhenius equation. So as you were referring, that if you have the higher temperature, if you want to find the permeability at different temperature, if you have this relationship, then you can determine the permeability at any different temperature of your storage or processing. So this is the method that how do we measure the permeation. So I remember one of you were saying that you had the demonstration of the instrument. What kind of instrument that was? Do you know the principle of that instrument? Anybody?
Depends on permeation only. Means we take a salt solution, cover it with that means whatever material we need to take, and then put into 0% RH or 100% RH. In that condition, whatever weight loss is
So you're talking about permeation of what, vapor or gases?
Actually, this is used for vapor, sir. Mostly using that material for silica gel. Change in the weight with the time and at different RH conditions.
Okay. So maybe is this one?
Yes, sir, this one.
Yeah, so you have some sort of a dish, in this case aluminum cup, or it could be made of any material, and then you have the desiccant inside. If you have a desiccant inside, you have some headspace also here, and the desiccant, and this is really dry. And if you said silica gel,
Yeah, silica gel.
so do you know if very dry silica gel what kind of relative humidity it would maintain? No, it's not really 0%. It maintains actually about 20%, 0.2 water activity at very low, unless you do really bone dry, which we don't do that. So you usually put in your hot oven, 70-80 degrees C for a couple of hours, and then you see the blue color, right? Yeah, so that time it gives you about 20% relative humidity. So you put in this cup, and then of course you put your film for which you want to measure the water vapor transmission rate. And then outside you can have very high relative humidity, typically 90%. So you would have a big desiccator. In that you can put water in the bottom and allow it the environment to saturate. In that you add this cup. So outside you have very high relative humidity, inside low relative humidity. So the partial pressure of vapor is very high outside and low inside, and it will allow it to transmit through it and is going to absorb by the desiccant. So here it tries to maintain kind of a low relative humidity, so you have the good driving potential. And then this is the kind of the graph you will get. So slowly the weight of this desiccant will increase because it is absorbing so at certain regular interval of time you measure the weight, and you would see it kinds of follows this curve. So after some times you will see steady state conditions, keeps on absorbing the same amount of water, and that slope gives you kind of water vapor transmission rate. Of course you need to have this gives you how much weight change with time, but if you divide it by the surface area, then it gives you water vapor transmission rate in terms of the gram per meter square per day, or whatever time you have on this x-axis. What is the other method for the same measurement we can use? I remember you were saying 100% or 0%.
something like that. Only the figures are.
So in other method, rather than having a desiccant inside and high relative humidity outside, you can do other way around. You can have water inside. If you have water inside and leave it for some period of time, what will you have? 100% relative humidity inside here. And then outside, you can put silica gel in the big desiccator. Outside you put silica gel, then what will happen? Outside you will have a low relative humidity, and inside you will have very high relative humidity. And then what will happen? You have the migration of vapor from inside to outside, and then with this migration you are going to have the weight loss, right?
Sir, how we can maintain with help of water 100% humidity?
Well,
Normal condition it is around 70 to 75% RH. To increase the humidity with help of water, you have to increase.
no, you leave it for a long period of time, then you will have the saturation. If you take water in any cup, right, seal it, you allow it sufficient amount of time, then it's going to produce 100% relative humidity there inside.
Because we measure for 30 to 40, it is around 70 to 75%.
No, if you allow it for sufficient time, then it's going to produce very high relative humidity. Well, you have learned the water activity concept, right? So in water activity concept, what do we have?
Equilibrium RH by 100.
Yeah, so you will get 100% relative humidity. Yeah. So this is the gravimetric method for measuring the water vapor transmission, right? So you are measuring basically the weight change for this cup, right? Whether it's desiccant, you have weight gain, but if you have water, then you will have weight loss. That's very easy to measure using balance. But if I had to measure this for the gases, how can we do that? So have you seen any instrument where we do for the gases?
Oxygen transmitter.
So if we are studying rather than the water vapor, let's say we are studying the gas exchange, of course you had to have a different partial pressure this side, then you will allow the exchange of gases. But then how would you quantify how much oxygen is being transmitted? Can we measure the weight? So what would be doing? Partial pressure. Okay, and how would you do that? So you have the sensors. So that's what we do with measurement of the oxygen transmission rate. So this is giving you just a schematic diagram. Usually it consists of a big cell. In that cell, you have this film, that's your sample. The upper side, in that cell, you purge your Permian gas. So in this case, it could be CO2, it could be N2, or it could be O2. The most important, our interest to us is actually oxygen. So you're purging the oxygen here, right? And then the lower chamber, you purge with carrier gas. It could be nitrogen. So for example, oxygen is coming through this, and here if you are purging with the nitrogen, so you would have very or almost no partial pressure of oxygen. Okay, so then you are very low partial pressure because you are purging always with the carrier gas. So as carrier gas is going, it is picking up because of the low partial pressure of the oxygen. The oxygen diffusion will happen or permeation will happen, and then you collect carrier gas or Permian gas here, and using some sort of a sensor, a detector, you detect how much is the oxygen is being coming through this film. And if you do this measurement, you will see the graph like this. After some time, initially there will be small amount, but then it will reach to the steady state, and that steady state you would have this value of how much oxygen flow is happening, and that's giving you amount with per unit time. And then you would know the surface area of the film, you know the thickness of the film. Using this information, you can calculate the permeability of the film. The other method, which is known as a quasi-isostatic, is temporarily isostatic. So in this case, the difference is that in the top chamber, again, you have the Permian gas going it. But in this case, you are not allowing carrier gas to flow it, but you are continuously collecting. Okay? And then your graph will show like this. And then in this case, after some time, you will have a steady state. It will come at certain flow rate. And then actually the amount which is you are collecting is increasing with time. So in this case, you are not measuring flow rate. Actually, in this case, you are measuring the absolute amount. and that at any given point, you know the amount has come, what time it has taken for that amount, and then from that you can find the flow rate, and of course again the surface area of the film and thickness of the film together, you can find the permeability. Okay, this is the general information about permeation of gases through packaging films, some fundamental concepts, and then how do we measure that permeation of the gases as well as vapor. Many different polymers we have, actually we have hundreds of different polymers, but for food applications we have some 8 to 10 polymers which are used for food applications. In that we do have a range of permeability or the oxygen barrier property or water vapor barrier properties. Most of the time we are able to select films which are suitable for giving the desired shelf life for selected food products. But some examples like sterilized product, you do vacuum packaging, and as you know, for high pressure as well as microwave processing, you have the polymeric film as a packaging material, and you want extremely high barrier. In fact, theoretically you want infinite barrier properties, but none of the polymer gives you infinite barrier. They give you still the finite barrier. It means that it does allows you some amount of water vapor exchange as well as oxygen exchange. So scientists and engineers have been working towards improving the barrier property of those polymeric films. And one of the concepts which recently has been tried, especially at the lab scale, to incorporate nanoparticles into the polymeric structures. Have you heard about this, nanoparticle? So these are actually nanoclay. These are derived from the rocks, and they have the platelet shape. Platelet shape means in one dimension the distance is quite long, about 100 to probably 700, 800, 900 nanometer, while other two dimensions they're just like a 1 nanometer. Right? What is nanometer? 10 to the power minus 9 meter. And if you incorporate those, so this thickness is showing you the thickness of the film from here to here, and in that thickness of the film, if you distribute these nanoparticles like this, then, and these nanoparticles, which are basically nanoclay or nanoplatelets, they are crystalline in structure, and the rest of the polymer is actually mostly amorphous. So if these nanoplatelets are not there, then what will happen? The gas will simply diffuse like this. But if you have the nanoplatelets distributed in polymeric structures, then if the gas would come, it will come like this. It tries to find the gap, and then it will travel like this. Because these platelets will not allow any gas diffusion. So gas has to move around and find a path, and then eventually comes out like this. So with that process, what you're doing, you're increasing the path of diffusion. And if you increase the path of diffusion, means it's going to take you longer time to diffuse. It means that it's going to reduce the diffusivity value. And if you reduce the diffusivity value, it is going to reduce the permeability, right? So that is the theoretical argument for improving the barrier property of the polymeric films. However, when we started doing the real production of these polymeric structure, we found that these nanoparticles or nanoplatelets actually tries to aggregate rather than distribute into the polymeric structure. So sometimes you have aggregation. So same number of platelet, if they aggregate, you would have like this kind of a structure. If there is a more aggregation, then you will have this kind of a structure. And imagine in this case now the gas would come here. This is how many blocks you have, 1, 2, 3, and then it's going to go like this. So it's not going to increase significantly the path of diffusion. In this case, probably there's only one block and then it's going to easily diffuse. So the change in the diffusivity would be much higher if you have this structure, and the change in diffusivity would be much lower if you have this kind of distribution of those platelets. So another difficulty in this point is that if these platelets are horizontal, then it would provide some restriction. And imagine if these platelets becomes vertical, then what will happen? It will not have any advantage. The gas will simply go through this parallel to those platelets, right? So any degree of angle if you have, then it is not good in terms of the barrier property. So this is another slide showing the computer simulation. So if you have very high angle, like in this case horizontal, then you will have a lot of obstruction. But in case if you have, it's the other way around. Actually, this is coming from left to right rather than going bottom to top. So in this case, actually, these are blocking more like perfectly horizontal in compared to the previous figure. But in this case, it is vertical because gas is diffusing from not bottom to top, but from left to right. So then in this case, you will have higher gas concentration here, lower gas concentration here because red is higher and it's diffusing in this direction. So it provides a lot of obstruction to the gas diffusion. So it is coming here, going through this like that. But as you start increasing the angle, then you will find that the diffusion is more because it is not providing any obstruction to the gas diffusion. In terms of the quantitative information, for example, this graph is showing that if you have 3% of this platelet distributed into the polymeric structure, and this is the aggregation width. If you have more and more aggregation, then the relative diffusivity is close to 1, and close to 1 means that it is not allowing to improve the barrier property, because this y-axis is showing the original diffusivity D0, and in numerator is the change in the diffusivity due to nanoplatelet. So if becomes 1, it means that both are same value. So what we are looking is the as low as possible. So if you have less and less aggregation, then you have more and more decrease in the diffusivity. So this figure is for 3% platelet, and this is figure for the 5% platelet. And 3 and 5% means that the 3% volume of the nanoparticles compared to the polymeric structure. And this is showing the effect of the angle. So if you have 90 degree, means this is parallel to the diffusion, then you will have absolutely no advantage. But if you have 0 degree, which means your platelets are horizontal, then you would have a significant reduction in diffusivity. This is another figure showing this effect of the aspect ratio. Aspect ratio means is the length of the platelet compared to the thickness of the platelet. Thickness is a 1 nanometer, and then in this case length is quite high compared to the thickness. So higher the length of the platelet, more is the reduction in the gas diffusion or diffusivity. Okay, and this is just showing when you have intercalation 1 and intercalation 5. It is just the aggregation is showing. If the aggregation is very little, then you have more reduction, and if aggregation is higher, then you don't have as much reduction as when you have the more distribution or even distribution of the platelet. So this is again the same figure, but showing in terms of the percentage of that platelet. So as you can see that a small amount such as 2 to 3% can significantly reduce the barrier property. After that, these platelets does not help much. So actually 3% of amount is sufficient to create very, very high barrier property in this nanocomposite films. And if you reduce the barrier property significantly, then how much reduction it will happen the the gas which is being transmitted from outside to inside. This is some theoretical calculation based on certain dimension of your package in terms of the surface area, in terms of the how much percentage of the nanoplatelets are there, in terms of the aspect ratio, and the intercalation or aggregation. And as you can see here, you could have, let me see, in case when you have the control film, let's say when you have no nanoparticle incorporate, it will have this amount of gas, which is 37.8 cc of O2 per year in a given surface area of the film or package. From that you can reduce as much as to, let's say, 1.4. Yeah, this is the smallest number. So if you have no aggregation, like a perfect distribution of nanoplatelet, which is W is equal to 1 nm, 1 nanometer, and then percentage loading about 5 to 7% of your nanoparticles, and the aspect ratio of 1000, then you would have such a low amount of gas being transmitted into your package compared to this. And with this, if you can see that 1 order of magnitude lower oxygen ingress in the package, and that can increase your shelf life significantly. So this is how improving the barrier property of the film can really significantly improve the shelf life of your product, because the overall gas transmission in 1 year would be dramatically reduced by improving the barrier property.